Okay, good morning everyone. I am glad that you are here. I have pleasure to open second day of our Symposium Industry 4.0. So on behalf of Dean Tomasz Chmielewski, of course I want to welcome once again, and I hope that today discussion during this symposium will be also very fruitful like yesterday. And I hope that you enjoyed last gala dinner. I think it will have bring you the nice Polish cuisine, and of course you spent a wonderful evening. So today the first keynote speaker is our guest from Hungary, Tamás Rupert. The presentation will be dedicated to the operator 4.0, so which is basically very important nowadays, especially in the Industry 4.0 and Industry 5.0 terms. So please, Tamás, come and present your, I am more than sure, that interesting speech. The floor is yours.
Okay. So thank you very much. Good morning for everybody. Thank you for joining to us this morning. So as I'm coming from the academic side also, we are really like a good keyword. So I just bring you another 4.0 behind the Industry 4.0. So I would like to say some words about the Operator 4.0 to you today, and I will try to explain what is the most important thing during the next industrial revolution. But first of all, we need to clarify what is this operator. So the operators are the human workers on the shop floor. Why we need to talk about human workers when we talk about industries, manufacturing? You know, we are just on the way on the Industry 4.0. We are talking a lot about the industrial automation. We are talking a lot about okay, never mind. We are talking a lot about robotics and, you know, industrial automation. But, you know, what is the main problem during the Industry 4.0 or during the industrial digitization nowadays? The main problem, let's say, the main problem we are. So the main problem is the humans, because we are, you know, we are really creative when we just working on the site. And it's really hard to predict what we will doing in the next step. So I will show some explanation how can we handle the human behavior on the shop floor, and how can we make a better collaboration between the industrial automation and between the humans. So beginning of the Industry 4.0, there was a lot of, let's say, afraid, you know, the industrial automation will stole our job, the robots will stole our jobs. To be honest, yeah, there are some victims. So we lost some job title on the shop floor. We just changed some human workers with robots and with I don't know, AGVs and etc. But the real question, so do we really want to keep our job in the present form? And this is what talk about the Operator 4.0. So how can we make much more efficient, how much more, I say, better workplace to the human workers, not just on the shop floor, but in the, you know, in the whole industrial area. So what is the problem with automation, with the industrial automation or any automation? The problem is, again, the humans. We are the problem because we are not so predictable, and we have also, you know, some new problems, some new challenges what the industrial automation should be handled. So what tools we have right now? We have a lot of AGVs on the shop floor. We have a lot of conveyors, and also we have a lot of cobots. So with the collaborative robots, yeah, they can save us So they are right now not dangerous. So we can work together with the collaborative robots, with the cobots. But the question is, how can we make the best coworker, and how can we make a better coworker with these collaborative robots? So if we just ask this question, so I have a collaborative robot here. What can I do with that right now? So I can tell him, okay, just give me a screwdriver, just give me the next raw material. And yeah, the collaborative robot just give me the next item, what I ask from that, you know. But this is not a good coworker, because if I have a coworker and we have a really good cooperation and we have a really good collaboration, in that case, I don't need to make any suggestion to him or today, you know, because my best coworker just capable to read in my mind and just capable to predict my next activity. And this is why I say that the collaborative robots right now in the present form is not the best coworker, because they are not able to predict my next activity, my next task. Okay, and this is the main challenges during the next generation of collaboration. And this is how can we define the revolution of the human workers. So this is now, you know, the operator 4.0. This is the fourth revolution of the human workers. You can see we just made some steps in the past. But during the operator 4.0, we want to make better support for the, you know, the human workers, the humans on the shop floor. How can we do that? We have a lot of predefined action and a lot of predefined tools. This term is coming from Professor Romero from the 60s. They are defined, you know, the super strength operator, where we have this exoskeleton to support the workers. We have the augmented operator, the virtual operator, where we can use or utilize the virtual reality or augmented reality technology, you know, because just in case of the digital twin, we really need real-time information from the operator, and we really need a real-time feedback for the operator. And for that, we can utilize the augmented reality or virtual reality or etc. The other really important thing is the healthy operator, because the new initiative of European Union is we really need to measure how the stress affect on the human workers. And if you're just looking a little bit in the literature, you can find a lot of research topic about, you know, there is a really good point for where there are really good stress for the human workers, and there are really bad stress factors for the human workers. And we are able to measure these stress factors, then we can make a more productive environment for the operators. Okay, and of course we just here with the collaborative operator, where yeah, we can utilize these collaborative robots. So the operator 4.0 is not just about how can we support the industrial workers, but it can be used in many other fields, like, you know, the miner 4.0 or space 4.0 or soldier 4.0. So we can utilize these tools in many different ways and in many different topics. Okay, so if we just talk about the analytical operator or smarter operator, then we need to talk about how can we utilize the artificial intelligence, not to stole our job. You know, we don't want to make a lot of victims of the AI. We want to support them with some good solution. So how can we utilize the tools of the artificial intelligence in case of if we want to make a better collaboration between the human workers and between the automated production system? So for this, there is one really important thing, we need to understand what the human workers doing right now. So we need to see, okay, you're doing this task right now. In the past, you do in the next time, I don't know, the task B. And in this case, I can predict, okay, if you are doing the task A, I can predict you will be doing the next step, the task B. And you need for the next tasks, I don't know, some collaborative robot arms or AGV or etc., some new raw materials. In that case, I can make a better scheduling or a better optimization scheduling for you. And of course, we can utilize this prediction and this recognition. You can see a two-way connection between these two blocks. So if I can recognize what are you doing right now, and based on some kind of event logs or some kind of historical data, I can predict your next activity. Then, you know, in the next steps, I can recognize your activity, and I can validate my prediction based on your actual recognized activity. Okay, so this is, let's say, a feedback system where we can teach our algorithm, or it just can, you know, self-learning from the real-time sensor data. Okay, and you see, for the activity recognition, it's really important to measure basically everything what I just can on the shop floor. Because it's really hard to say what are the people doing right now. Of course, in that case, I have, you know, some work schedule or some work instruction for the current operator. Then it's a little bit easier. But as I said in the beginning, the humans are really stochastic behavior, you know. So to measure and to recognize the activities, we need a lot of sensors. And also we need to measure not just the operators, but the environment and also the machines. Because if we just merge this data, then, you know, we can make a more precise monitoring system. Okay. What is the main challenges right now? If you are doing, I don't know, some Industry 4.0 development on a real industrial environment, you are facing with a lot of different kind of machine, with a lot of different kind of environment. And this is what we call some kind of brownfield Industry 4.0, where we have a lot of legacy machines, we have some new machines, but the new machines are also coming from a different you know, manufacturers. So we have a lot of different machines, and we have a lot of different systems on the shop floor. Fortunately, in our university, we have a really legacy laboratory where we can make some, let's say, brownfield industry measurement, or we can say that we can make some retrofitting technology and make better, you know, monitoring system for that. So we really like the old machine because there are any sensor on the machine, and we can play around it a little bit. But I believe it's really important with the new machines also, because what's happened if you just buy a new CNC machines with, I don't know, thousands euros. Yeah, you got the machines, you got hundreds of sensors, but what you didn't get, or what you don't get, the database and the software together and analyze the sensor data. For that, yeah, you need to buy a database, a cloud system, but you don't, you know, you have a lot of different machines, so you need to buy a lot of different databases and cloud systems. So it's really expensive and, yeah, and not so easy. So this is also where we can utilize this, some kind of retrofitting technologies. Okay, so we have these laboratories, we have some kind of digital twin in there. I will show some details about it a little bit later. And we just doing a lot of measurement there. But why are talking about the brownfield industry 4.0? because this is one of the main pillars of how can we utilize the operator 4.0 terms or applications in real-life scenarios. These three pillars could be the main pillars of the extended, let's say, extended operator 4.0. You know, this one is the brownfield industry 4.0. With these methods or technologies, we are able to measure the main KPIs, you know, the main indicators from the shop floor. With the operator 4.0 we have a lot of tools to support the human workers. And what we need to also do, make some database model, and we need to some discovery algorithm for them. So we can utilize the human digital twin, we can utilize the machine digital twins and environment digital twins, and a lot of other modeling technologies. Okay, I just want to show you some example of our sensor technologies there. So we measure the accelerometer, but not for the you know, vibration analysis. We just want to discover what, let's say, state, what is the current state of the machine. So what I mean about the state, not the health state, so it will be, I don't know, broke in the next 5 minutes. I mean about the state, yeah, now it's working, now it's waiting, now it's, I don't know, it's a changeover, now it's something other happens. And we can easily measure with a really basic accelerometer sensor there. So what you can see in the right bottom, you can recognize some different characteristic of the sensor signal, and all of these different characteristics just represent one working step on the machine, because all of the working steps just, you know, working with some different kind of parameters on the machine, and we can recognize that easily. Okay, I suppose if you were any time in a manufacturing, you see a lot of color lamp there. These are the handle lamp. And I don't know what is your experience, but my experience is, okay, we just talk around, okay, what digitization you have. Yeah, you have the handle lamp, okay, but you know now 2 handle lamps just in red. This is something that happens. Okay, but you recorded this signal or not? No, this is just a visualization. We need to see where is the problem on the shop floor. But we don't have any database for that, because these are just an analog system. You know, I push the button, it just turns to red or blue or yellow. So for these, we just developed a really simple sensor to measure what kind of color is just, you know, lighting up on the end-on lamp, and we can gather this information from the shop floor with a wireless sensor basically in real time. The next sensor is, let's say, the mobilized sensors. We have an own developed, let's say, AGV in the laboratory. And also we have an indoor positioning system, which is some kind of indoor GPS, so we can measure the position of the sensor you know, during the movement. So we can measure the position, these AGVs in the laboratory, and we have a lot of sensors on the AGVs, so we are able to measure, I don't know, the temperature, the humidity. But the most important thing is the main problem with the indoor positioning system. So it's really amazing. You can measure all the movement, all your assets, all your products on the shop floor with this indoor GPS. So you have the full traceability of everything if you want. But what the main problem? The main problem is one tag is around 20 euros or something like this. It's a little bit high for any industry, because you want, I don't know, 2,000 species. You know, the price is just go away. So for that, we are trying to utilize the RFID technologies, which is really cheap. But the tags are just passive. But we have the indoor positioning system on the RFID reader, the mobilized RFID reader, I'm able to measure the position of the reader, and the reader are able to measure, what kind of RFID tags around the reader. In that case, I can make some sensor fusion, and I can say, yeah, in that place there was, I don't know, 5 different RFID chips. And also, we utilize the LiDAR technology, so it's just to make a better map of the laboratory and just to make it, let's say, real time. So this is how we try to build an intelligent space in our laboratory. The intelligent space is just about, we need to monitor everything and we need to control everything basically in real time. Okay, so in the intelligent space, yeah, we have some different level, for the shop floor, for the decision-making procedures, and etc. And finally, I want to show you one example from a real manufacturing era. It's coming from the wire harness company where they are just produced, the big wires for your cars. Why is it important for us? Because they use a lot of human workers on the shop floor because the wire harness production are not really robotized right now. So they have this conveyor line, and we are able to measure, every operators on the shop floor and every product on the shop floor. And what we do with this information, first of all, we just modeling the movement of the operators. This is on the left button. So we are able to measure the movement of the operator during the assembly table, and we are able, based on this information, to predict the next movement in the next task. And why are we do that? So if we are able to measure the activity time on the assembly table, because we have some really simple sensor to do that, then we can predict the finish time of every cycle, and in that case, we are able to manage the cycle time on the conveyor line. So this was our first, let's say, real-life digital twin, because we have a real-time data from the shop floor, thanks for the indoor GPS. We have a system model basically on a Raspberry Pi, implemented in Python, and we are able to control the PLC of the conveyor line with this really simple Raspberry Pi. So we just make an example and an application for the wire harness company. We measure the operator and the products. We calculate the optimal cycle time for the conveyor line, and we just control the conveyor line via the PLC. Yeah, this is our digital twin framework where we have a lot of inputs, and we have some optimization toolbox, and our outputs, yeah, will be the KPIs and also the control parameters. Because my time is ending shortly, I want just one takeaway message for you. So this is, I think, what talk about the operator 4.0, and I hope it will be talk about the industry 5.0. So yeah, humans should never be subservient to the machines or the automation system. We need to, the machines and the automation should be the servant to the humans. And I know it's just a dummy meme, but the truth behind the meme is really important. So we really need to make a clever collaboration between the humans and the robots. And, in the next revolution of industry, the main focus will be the human workers, and we need make some better support for them, because, every time the humans is the most important thing. For that, we call a research network behind the operator 4.0 with Professor Romero, and also thank you, Bart, to invited me to here. Bart is also a member of this research network. So you can see our call for collaboration on the website, but our purpose is make the industrial make a more human-centered place again. And thank you for your attention, and I'm really curious about your question. We have 4 minutes left.
Thank you very much, Tamas, for a very interesting presentation. Do we have some questions? Okay.
Hi, it's Miro from WUT. I like your presentation very much. You told about the brownfield at your laboratory. Do you have some experience with taking information from PLC of the machine, from the control system? Or only this is from sensors like accelerometer, microphone, or something?
Yeah, thank you. Yeah, the PLCs are really tricky because we need a lot of technology for them and a lot of interfaces, and so no, we don't have too much experience with the PLCs. We are really into just some really simple and cheap own developed sensor and measure not directly from the machines, but just on the machine, because it's many times there are no PLCs or we are not able to connect to the PLCs. But yeah, it's a really good point. If we can connect to the PLCs, that's the better way to gather the data. Thank you.
Any other questions? Professor Maki?
Thank you, Tamas, for the very interesting presentation. Just a comment on the question on the application in small and medium enterprises, which may have limits in terms of human funding, financial, and so on. Do you think that your approach can be sized and you have experience in this?
My answer is yes. My longest answer is yes. So this some kind of brownfield industry 4.0, it could be the best way for the SMEs, because in my experience at least, the SMEs are struggling with the legacy system. And also, if you have now some funding money, you will buy a new machines, but after next year you got again some money, you will buy other machines from another company. And this is why they are just struggling with with the MES, with the ERP, because they have a lot of different kind of technologies on the shop floor. And this is a real challenging to gather all the information in just one system. And yeah, the Operator 4.0 solution. So I know these augmented reality and virtual reality, so we are not there right now. I see a lot of examples in a big company, but this was just a demonstration, not in a real life scenario. I believe the tools of the Operator 4.0, there are some simple method what we can apply there. Yeah, I don't know I answered the question or not.
No, basically, I had an impression based on an experience we're having on the workers in medium-sized enterprises, and the project regards safety, which is also related to the cases. So it may depend on the fact that the asset is fixed or mobile. And of course, some technologies were applied considering the low cost or the affordability for the SME, while others are not. So for example, augmented reality was not applied. That is some consideration that we can discuss more in the future.
Thank you very much. Do we have some other questions? If not, maybe I will have one more question. Did you, Tamas, include in your research the resistance of the employees? Because, you know, not every worker won't learn new technologies. Not every worker feel very good in a totally new environment, especially with high level of automatization, digitization. So did you include this aspect in your researchers in your laboratory?
Yeah, thank you very much for this good question, because this is what Professor Romero just defined in operator 5.0, because we have the operator 5.0, of course. And this is talk about how can we make a more resilient operators on the shop floor. So yeah, this is the new way. We will see what happened there, but we need to handle this. But you know, I was used to be in some Serbian company, and they are just apply some methods from these resilience operators, but because what happens, just, you know, they need to shut down of the production line because of the engineers. I was the reason. They, you know, the supervisor just come up, okay, you don't have now the production line, now you need to clean the shop floor, so now you need to move on and just, you know, just make more productive and yeah, efficient. Yeah, thank you.
Thank you very much, and I am very happy that you include the society in your researches, because as Rodolfo yesterday said, technology is very important. Of course, we have very big advancement in this field, but without including social aspects or humans, society, it will be very hard to survive on the future. So thank you very much for your interesting speech. And the next presentation will be remotely by Professor Roberto Tetti from Italy. It will be about smart monitoring of machining, so I think it will be also very, very interesting. So we can welcome Professor Tetti, and the floor is yours.
Okay. Hello. Yes. I will start sharing my screen here. Can you see the shared screen? Hello? Okay. All right. So I can start my presentation entitled Smart Monitoring of Machining Trends and Challenges. Let me start by saying that in the cutting zone of a machining process, there are several variables which are influenced by process conditions like cutting forces, acoustic emission, noise, temperature, surface finish, and so on and so forth. F5, I have a Macintosh. Okay. What should I do here? Yeah. You don't see me speaking. Let me try this. Is it right side down corner of the Microsoft Teams? In the, yeah, I opened the, let me open again. I'm not sure. Can you see it, the full screen, or not? No. Let me try again. Let me try again. Let me just. Okay. Now, I don't know why when I go to Microsoft Teams, I lose the full screen. We'll try again. Yes, yeah, I realize. But I am now, I opened the PowerPoint in full screen, so I can see the full screen on my computer, but it doesn't go to Microsoft for some reason. Cannot say why. Oh my God. Well, what I can do here, I can just reduce. Well, what I can do, I can increase the presentation size. Yes. On my computer, I see it in full screen, so I don't know why. Let me see. If this is possible. Okay. Okay. This is. What? Okay. Okay. A problem with the setting. Let me also say that I have some echo coming back when I speak. I don't know if you can select. I mean, if this is a problem also for you, this echoing when I speak. No. Okay. Let me just go on. As I was saying, in the cutting zone, there are several variables influenced by machining process conditions like cutting forces, acoustic emission, noise, temperature, surface finish, and so on. Some variables useful for process monitoring can be measured by sensors. Then sensor signals are processed to obtain features well related to the process conditions to be monitored. Relevant signal features can be integrated into intelligent decision-making systems for final diagnosis to be sent to the machine tool controller to take the correct actions needed. Now, the sequence of activities in sensor monitoring of machining is summarized in this slide. So we have the process variables on the left, and through sensorial perception, we detect sensor signals. These signals are processed for feature extraction, relevant features from the signals. These features are sent to a cognitive intelligent decision-making system or paradigm in order to decide on what action to take. Now, going back to sensor monitoring, we can consider that measuring techniques in general can be classified into two approaches: direct measurement and indirect measurement. Now, in direct measurement, the actual quantity of the variable, for example, tool wear level, is measured directly. Now, this is very accurate, but mainly usable in a laboratory environment because of different problems like access problems, illumination problems, and so on. So, for example, we can use cameras, laser beams, electroresistance for this. Now, in indirect measurement, on the other side, auxiliary quantities, for example, cutting force components, are measured, And the actual quantity of interest, for example, the tool wear, is deduced via empirical correlations. Now, this approach is less accurate, but also less complex, and is more suitable for practical applications to evaluate process performance, to provide information for process optimization using sensors. The sensors and sensor systems used for machining process monitoring, the most common, the most utilized, are reported in this slide: motor power and current sensors, force and torque. These are typically piezoelectric sensors or strain gauges. There are also some other sensor types for force and torque. Acoustic emission sensors, high frequency acoustic sensors, vibration sensors, these are low frequency sensors. Other sensor types like optical sensors, cameras, temperature sensors, and so on. Now, again, the scheme of advanced sensor signal processing is reported in this slide. So starting from the left, we typically have from sensors analog signals. Now, these analog sensor signals certainly need pre-processing. And within pre-processing, we find filtering, we find segmentation, signals segmentation. We will describe this. We will have analog to digital transformation. So typically we obtain a digital time domain signal. Now, this time domain signal can be transformed into the frequency domain using different methods: fast Fourier transform, short time Fourier transform, wavelet transform. So in this way, we obtain a frequency domain signal. Now, with the time domain and frequency domain signals, same signal in time domain and frequency domain, now we can apply feature extraction, different types of feature extraction procedures. And we can obtain a large number of features. But these features characteristic of the sensor signals, they need to be selected in order to be subjected to feature selection procedure, in order to identify which are the relevant signal features among all the features that we have that are useful for the monitoring scope that we have. For example, tool wear level, residual stress value, chip form control, and other scopes. Yes, the monitoring scopes in machining processes are reported in this slide. Tool conditions, in the first instance, it's very common. Tool breakage, tool wear, process conditions, whether the process parameters are optimized or not optimized. Machine tool state can be monitored. Surface integrity in terms of metallurgical damage, surface and subsurface metallurgical damage, residual stress, or surface cracks. Chip form is also measured. Chatter detection is carried out, work material state, and there are also other specific monitoring scopes. Now, intelligent decision-making systems and paradigms, they are implemented using the features extracted and selected. Signal features obtained from sensor signals using advanced processing methods, and then selected to provide input to decision-making systems like supervised and unsupervised neural networks, or fuzzy logic systems, or other methods like genetic algorithms and colony and Bayes algorithms. Also hybrid systems combining together neural networks and fuzzy logic, for example, the so-called neurofuzzy systems. Now, it may be worth mentioning that when measuring a particular variable of a manufacturing process, a single sensory source for that variable may not be able to meet all the required performance specifications. A solution to this problem is sensor fusion. Sensor fusion is a technology that combines sensory data from different sources of different nature, so that the resulting information is better than would be possible when the sources are used individually. Now, we shall see some examples of this application, also sensor fusion, for case studies carried out at the Fraunhofer Joint Laboratory of Advanced Production Technology at the University of Naples. I was thinking of presenting 3 case studies: sensor monitoring and turning of nickel-based alloys, sensor monitoring and machining of fiber-reinforced composites, and sensor monitoring and turning of carbon steel for chip control. Now, because of the time constraint, I cannot present all 3 case studies. I will only refer to the first one, which is related to turning of nickel-based alloys with the scope to monitor tool wear and residual stress. Now, the turning of nickel-based alloys was carried out using a numerical control vertical lathe from a aero engine industry. The material was ECOLE 718 nickel-based alloy, typical of aero engine construction. Tool wear was directly measured through a microscope in order to measure, to detect the flank wear of the tool, in order to set up a training data set, a training base for the intelligent paradigm. Residual stress was measured using a diffraction X-ray technique. And again, these direct measurements were used to set up a training set. And the objective of the program was to find correlations between input parameters represented by sensor signals of cutting force and acoustic emission, and the output values, that is the tool wear level and the residual stress value. And the feature extraction technique applied to these signals, cutting force signals, acoustic emission signals, was based on the principal component analysis methodology. Finally, the intelligent decision-making was performed via supervised neural networks. In the experimental testing, we had standard cutting condition tests and severe cutting condition tests. In the standard cutting condition tests, the typical process condition, cutting speed between 45 and 55 meters per minute, feed rate between 0.1 and 0.15 millimeters per revolution, depth of cut 0.3, wet lubrication condition. These are the standard processing parameters used in industry, in the aero engine industry for this type of machining, ECOLE 718. But we also used severe cutting conditions, so much higher cutting speed, 80, 100 meters per minute. And we also used dry cutting instead of wet cutting, just to check whether these conditions were acceptable for the aero engine industry. And the duration of cutting steps in standard cutting conditions was much longer than for severe cutting conditions, 120 seconds for standard test and 30 seconds for severe test, because in severe cutting condition tests, the tool wear development was very rapid. The end of each test was when the maximum allowable wear length of 0.3 millimeters was reached. So this is the machine tool, the vertical turning machine that was used for the experimental testing, and the different sensors were mounted as near as possible to the cutting tool. So we had a force sensor providing the three components of the cutting force in the X, Y, and Z direction. We had an acoustic emission sensor. And these sensors provided analog signals that had to be digitized through a national instruments card, A to D card. And then we also used an acceleration sensor, providing the three components of the acceleration in the X, Y, and Z direction. This sensor included digitization in itself. Therefore, from the sensor, we directly obtain digital digital time domain signals to be stored on a computer or on a hard disk. Now, these are examples of raw signals obtained during testing. We have in the bottom the three cutting force components Fx, Fy, Fz, and higher in the graph the acoustic emission RMS signals. Now, these four signals are the raw signals. Therefore, you can see that at the beginning, at the end of this test and these signals, there are some parts of the signals that are not significant. They do not correspond to interaction between cutting tool and work material. So there is a need for a first segmentation. We need to cut off the head and the tail of these signals. And this is the result of the first signal segmentation. We removed same way in all the signals, the head and the tail of the signals. But a second segmentation was also applied in order to identify a signal area, the signal areas zones where the signal had no uncertainty like peaks or abrupt variations. So the yellow part is representing the second signal segmentation, and that signal part for all the 7 signals, cutting force components, acoustic emission, acceleration components, was considered for processing, data processing. But from each of these 7 signals, 5 portions made of 3,000 samples, represented here by the small yellow windows reported on each of the signals, on each of the 7 signals, were only considered for data processing. So data processing consisted, for feature extraction, was based on the principal component analysis methodology, which in general is used to reduce the high dimensionality of a data set consisting of a large number of interrelated variables, as well as to extract significant signal features to utilize for intelligent pattern recognition. Now, the structure of principal component analysis approach is described here. Typically, we have a number of sensors, P sensors, and for each sensor signal, we have N samplings, in our case, 3,000 samplings. So in output, we have N times P matrix, so 7 signals, 3,000 samplings. This multiplication gives the dimensions of this matrix. From the matrix, we calculate the covariance matrix with this equation, where Musabai represents the mean value of the original variable, sensor signal xi. And through the principal component analysis methodology, a set of new variables are found which are uncorrelated between themselves and present a reduced variance. These new variables are called the principal components, and they are related to the original variables, the original sensor signals, using simple equations like this one. For example, y sub I is one principal component and is related to the original variables x1, x2, xp through simple equations like this one. So how does it work, this procedure? We start with an initial data set You can see here in the first line, we have the 7 sensor signals: cutting force component Fx, Fy, Fz, acoustic emission RMS, acceleration components Ax, Ay, Az. And in the first columns, we have the 3,000 sampling for each sensor signal. So basically, again, 7 times 3,000 matrix, initial matrix, from which we obtain the covariance matrix, and we can evaluate the eigenvectors. You see in this third graph or table, you see in the first column, the 7 original variables, Fx, Fy, Fz, acoustic emission, Ax, Ay, Az, and the principal components, the new variables, first, second, third, fourth, fifth, sixth, and seventh. Now, by calculating the eigenvalues, we can rank the principal components. So the largest eigenvalue is related, it gives or represents the first principal component, and then as the eigenvalues are reduced, then we have in a ranking the second, third, fourth, fifth, sixth, and seventh principal component. This ranking also represents some relevance in the monitoring scope to be verified. So in the end, we have a table that correlates the original variables, the original signals, acceleration AY, AX, AZ, acoustic emission, cutting force Fy, Fz, Fx, with the principal components, first, second, third, fourth, fifth, seventh, sixth, and seventh. So we can correlate, we can know that the first principal component refers to the acceleration component in the y direction. Then we can use these features, these extracted and selected and ranked features to construct pattern vectors to be used as input to a intelligent decision-making paradigm based on a neural network architecture. And 3-layer feed-forward backpropagation neural networks were built with the structure described here. The input layer of a neural network contains a number of nodes equal to the signal features selected. The hidden layer had a number of nodes related to the number of input nodes. So the same number of nodes as the input node, or twice the number of nodes as the input node, 3 times the number of nodes as the input nodes. The output layer had only one node, yielding a coded value for residual stress or tool wear state. So 0 for acceptable residual stress value and fresh tool condition, 1 for unacceptable residual stress value and worn tool condition. Different input feature vectors were constructed and utilized by combining different types of sensor signals or features from sensor signals. For example, feature vectors containing only 3 elements, the 3 components of the acceleration, the 3 principal components obtained, or 4 elements by adding the acoustic emission, or 5 elements by adding the cutting force component Fy, or 6 elements with Fy and Fz, 7 elements with all principal components from all the 7 sensor signals. And the neural network configurations are reported on the right. So for 3 elements input feature vectors, we have configuration 331 or 361, 3 nodes in the input layer, 3 or 6 nodes in the hidden layer, and 1 node in the output layer. In the case of 7 elements, the neural network configurations were 771 and 741. This means 7 input nodes, 7 nodes in the input layer, and 7 or 14 nodes in the hidden layer. These were actually selected, constructed, and tested. And to conclude, the results of the smart data processing based on neural networks are reported here in terms of a spider graph. So on the left, with reference to tool state identification in standard cutting condition tests, we have very high success rates when we use either all 7 signals or 6 signals. Our success rates in identifying through neural networks the toolware acceptable, unacceptable toolware state was 98, 99%. This success rate decreases when we reduce the number of sensor signals. When we go down to only three sensor signals, only 3 variables, A, Y, X, A, Z, we go down to 85%, which is still a good result. In the case of severe cutting conditions, the success rate is reduced in comparison, but still quite high, higher than 90% when we use 6 or 7 sensor signals. We go down to 78, 80% when we use only 3 or 4 sensor signals. Similar situation we have for residual stress assessment. In standard cutting conditions, we identify the acceptable, unacceptable residual stress level with a success rate up to 90, 97, 98% when all 6 or 7 sensor signals are used. And even when we use 4 or 3 sensor signals, we never go under 92% success rate. In severe cutting tests, in this case for residual stress assessment, the success rate is still high when 6 or 7 sensor signals are used, something like 93, 95%. But when we use only 3 sensor signals, like cutting for component sensor signals, we go down to 75% success rate. To conclude, I wanted to show a similar application for two-way state in machining of fiber-reinforced composites, 3 different types of composite: carbon fiber-reinforced composite, glass fiber-reinforced composite, and sheet molding compound. In this case, the feature extraction was carried out through a parametric spectrum model evaluation by linear predictive analysis, and the decision-making was also based on neural networks. And the third application that I cannot present because of time limitation was chip form control in turning of carbon steel. Here, the feature extraction was based on wavelet packet transfer in the time frequency domain, and again, intelligent decision making was carried out with supervised neural networks. I think with this I can conclude, thanking you for your attention, and of course I'm ready for questions from your side. Hello?
I think also very impressive. But maybe if some questions or comments occur, we can send you this question via email. Okay? It will be, I think, more comfortable for you, and also consider the time limitation of this symposium. It will be much understandable. Okay?
Okay. Thank you very much. Congratulations. Thank you. Congratulations for the symposium organization. Thank you.
Okay, so now we have the next presentations. It will be the industry presentation. So Mr. Filip Bączkowski and Jan Rusiecki will show you the implementation of Industry 4.0 tools in a specific printing plant. So it will be very interesting for me because I also, with my research team, has some experience in this background. So I am very glad that you are here, gentlemen, and the floor is yours. I just opened the presentation. Okay. Yes. And F5. Sorry.
Thank you very much. Ladies and gentlemen, hello, my name is Jan Rusiecki. I represent DKR Consulting, and together with Filip Bączkowski from UDS, we would like to present our experiences in implementing personalized Industry 4.0 solutions at the UDS's printing plant. So quickly, our agenda is we will quickly present the characteristics of the production process at UDS, and then we will move to how the Industry 4.0 concept looks like in the context of UDS's process. After that, we will show you the methodology of implementing smart factory solutions, and we will end with an example implementation of the automatic planning, production scheduling. So I'll pass the microphone to Filip. Bliżej. Dobra, dzięki.
So hello everyone, my name is Filip Bączkowski and I'm business analyst in UDS company. We are specializing in producing POS materials and laminated packaging for 25 years. And our production is demanding because we only 15% of our project are repetitive, and the rest of them are non-repetitive. So they are unique and usually new. Our production, we produce 1.5 million square meters of cardboard, and this value is increasing because of our investings in machine park. We produce a lot of displays, and from our warehouse leaves 8,000 pallets per month. And in our producing process, every day we have 250 orders at all stages. Here we can see our producing process, and mostly it starts on pre-cutting, but I can say firstly the normal path of producing process, and secondly I will add something. So firstly we have pre-cutting, printing, laminating, cutting, shearing, cleaning and assembling. And sometimes after assembling it is co-packing, but it is normal path. Mostly we don't have normal path because our customers have some other needs. So for example, they want our product after printing, after laminating, after cutting, and so on. And we don't always have the product on the first stage. Sometimes the product is sending to us before printing, so it is not our material. And I will remind you that we have 250 productions orders per day at all stages, and it doesn't start and it doesn't end in the same stage. So the needs of our company are to optimize our process, to minimize lead time, to minimize the time of setup, of changeover time at the machine park, and to more efficient our human resources. our needs are to better react to failure on our production process. So we need a program or software which help us to be better fit on the market, and to be quicker when something goes wrong. We need to settle some expectation times for each process, and we need to make some indicators which help us to account and assume a worker, machine, and so on. So we need to be more automized, predictive, and we have kindly asked to help DKR Consulting.
Thank you very much. Oh, sorry. Quickly, this slide quickly presents the concept of Industry 4.0. I'm sure the distinguished audience is well aware of what exactly Industry 4.0 means, but just to simplify quickly, Industry 4.0 as the combining of information technology and operational technology. But in the context of UDS's process is the need of mass customization and with low-cost manufacturing, as only 15% of UDS's orders are repetitive projects. So how did we approach this problem? We looked at RPA and RDA, which are robotic process automation and robotic desktop automation, and we thought, if these are used in shared services centers and business process outsourcing companies, our train of thought was, why not use it for production planning and scheduling? And that's how the RPPA concept was born, robotic planning process automation. So with this concept, what would be the key requirements to successfully automate process production planning? So we need production times, machine performance, changeover, all the data related to production, as well as infrastructure. But the most important thing is the data and the reports with MSA, OE. So the crucial thing is the implementation of a mass or data acquisition system in order to acquire this data and to verify it. So that was step one for us, the data acquisition. This slide shows the number of technologies that we used, ranging from traditional database solutions through cloud technologies and just a wide range of IT technologies were used in the project. But first of all, as data acquisition is our first step, what would be the scope of preparatory work? So a signal acquisition, we can use existing sensors, we can use signals coming from control cabinets through relays and contractors, as well as PLCs, which were already mentioned today in the Q&A session. Second thing is determining the logic of the acquired signals. So we see a digital 1 on the sensor. How do we know that the machine is actually operating and it's not in a changeover state, for example? Secondly is, if needed, is the selection and mounting of additional sensors. This is especially important if there's need for analog sensors that need to be finely tuned. Additionally, customizing the data acquisition device, and trivial things like infrastructure, wiring, which might sound simple, but when you have a big factory, there's kilometers of cables, as well as the challenges of providing internet access and the optimal place for data acquisition devices. So a little bit about our hardware software solutions. So we used Raspberry Pi as the brain of the device with custom data acquisition hardware and custom Linux-based software with a custom enclosure. We are ready for industrial standards 12 or 24 volt signals, as well as supporting digital and analog sensors. And the device is plug and play. After you connect it to the internet, it's plug and play, connects to our cloud. And in case of connection loss, the data is cached locally on the Raspberry Pi in a Redis NoSQL database. So once we have the data in the database, as I mentioned earlier, we need to interpret the data. So for example, in one of the processes of UDS, we have glue plotters that dose glue, and we are unable to mount a sensor that would specifically tell us how many sheets did the glue plotter process. So based on the signals, we developed an example of an interpreter that, based on the glue doses, counts the sheets that were processed by the glue plotter. So this is one of the main challenges with raw data. Secondly, the challenges with joining or merging data from the ERP with real-time data from the data acquisition system. And in case of UDS, it was the challenge was how do we replicate the data from the ERP database in a way that does not disrupt operating of the ERP system itself. So we don't want to, in basics, we don't want to kill the ERP database by our replication. So, but after solving the challenges with data acquisition, we started working on forecasting order execution times. So for some processes, for some industrial processes, the normative times, the standard times, can be derived from the maximum possible number of machine cycles per time unit. Alternatively, you can use Pareto 20% of production times for the same type of order. However, in printing and binding processes, the time and the performance of the process can depend on many factors simultaneously, namely surface area, number of colors. So it is necessary to implement AI tools to forecast execution times. So this is an example of forecasting of automated flatbed die cutting, where we have data from the machine itself, the settings of the material in our database, merged with sensors, merged with ERP data, and through regression tree models, we were able to forecast lead time for the process. And through continuous analysis, we can automatically adjust our forecast in case of process improvements, change of settings, change of material processes or human resources. Now moving to production scheduling. So from the database, we already have parameters required to successfully schedule production. However, we also can have a few optimizations that we can schedule for: punctuality, lead time, machine park utilization, human resource utilization, or overall process costs. And through genetic optimization, we were able to implement such a model. So in the first stage, at the prototype stage, we use greedy algorithms with forced order scheduling based on a ranked list. And these were Microsoft Excel prototypes. Based on that, the UDS's internal IT department implemented our prototype as a module for their ERP. So this is how the production scheduling system looks at the moment, with two phases. First one with prototype algorithm by forced order ranking, and second phase with scheduling by lead time, machine park utilization, and other goals. Through that, we were able to successfully schedule 250 production orders a day. So before implementation, there were two planners that would work 8 hours daily, continuously extinguishing fires with manual and mistake-prone planning, problems with rescheduling the plan in the event of any plan insertions or disruptions. And additionally, there were problems with evaluating the performance of the planning and manufacturing departments because they would usually blame each other for any failures that would take place on the shop floor. Currently, the planning process has been shortened to a few seconds. All relevant factors are considered in the plan, and the planning robot is resistant to any external pressure with all online updating of all the required data. And through this project, the organization is prepared to work with future AI-based solutions, and it also improved process awareness. Thank you very much for your attention. We're open for questions.
Okay. Thank you very much for interesting presentations. Maybe we have some questions. Come on, please don't be shy. We have a delay, okay? But 1-2 questions we can ask.
Yeah, thank you very much. So you just mentioned you use a lot of AI tools there, and your colleague just mentioned you have a lot of anomalies on the shop floor. So now you have a lot of data, maybe some kind of event log from the production. But my question is, do you ever consider about use the process mining or sequence mining to discover the whole process and the anomalies? Yeah.
Right now we do, with merging of ERP data with real-time data, because ERP data currently, as it is in the system, is manually entered. So all the times, event times in the system, they can have an error related to the fact that the human operator solves the problem, then inputs everything in the system, and we get the timestamp of when the event has been finalized. So only after merging real-time data from the sensors with ERP, we can proceed to deeply process mine.
Okay, some other question? If not, thank you very much for your presentation. It was very nice. And before the coffee break, I want to invite to the presentation my friends and my colleagues from WUT, so Aldona Kluczek and Krzysztof Krystosiak, and they will tell you about, I think, very interesting research initiative, research group, Sustain 4.0. So the floor is yours.
Thank you, Krzysztof. Hello, everyone. Good morning today, and in this second day, I would like to show you our presentation of our team. Sorry, testing. Sustain 4.0 is a sustainable Industry 4.0 initiative, and we are the part of the team, me and my colleague Aldona. We will be present today our research initiative and the whole team. But first, short agenda. I will describe a little bit about our research team. Then I will go to the introduction. Next, Sustainable Printing 4.0, our initiative. Then some problem statement and research questions. Next, extended research and some results. So, I mentioned about our Sustain 4.0 research team. So this is our whole team. Bart is our team leader. But of course, our research team is not closed. So we are open for any initiative. And of course, using this QR code, you can easily search our website, our email, and we invite you to cooperate, of course. So this is the scope of our Sustain for Zero research group. Modeling relationships of sustainability and Industry 4.0 or even 5.0, because of course we are not staying at the same place. And what we are focused on? We are focused on qualitative and quantitative diagnosis of sustainability and Industry 4.0 for discovering qualitative and quantitative relations of sustainability and Industry 4.0 and some methodological aspects of sustainable Industry 4.0 applicants and deployments. Our mission and vision is to conduct scientific research and deployment and promote knowledge on sustainable Industry 4.0. And we would like to be a team globally recognized, cooperating with the international respected research entities, as well as publishing in the journals with high impact. That's few things about our team. So now the motives and challenge which was developing during our team. So first, customer expectations, Industry 4.0 in the printing industry, sustainability practices in the printing industry as well, and some environmental considerations. As an introduction, we of course can see approach of triple bottom line that we already know that Industry 4.0 approach has a lot of benefits. Yes, we already know these benefits. There are plenty of benefits, but as well as some concerns. And on this slide, you can see some based expected benefits from three parts of triple bottom line perspective approach: economic, environmental, and social, and some concerns, of course. And there are many of concerns as well as many pros. So, of course, this list is not exhaustive. So, our approach is sustainability from one side, Industry 4.0 in printing, because we focus on printing and packaging industry, or packaging, we call it printed packaging. And we built a first model of our research, and we call it Sustainable Printing 4.0. And today I would like to show you some our primary research, and as well as expected, you will see. Some problem statement and research methods. To what extent are Industry 4.0 technologies used in the printing and packaging industry in Poland? And do they support the implementation of sustainability development practices? That's problem statements for our research. And we divide this for the initial research and extended research. These are research questions for our primary research. You can see them, but I will describe them in details on the next slides, and I will show you the result of our research. Of course, first of all, our research sample, because first primary research was conducted as interviews, very extended interviews. Each interview takes approximately 45-50 minutes with corresponding people from the printing and packaging industries. You have these industries here, but without, of course, name, because of the name of these companies are confidential. Only interviews, positions, and the size of the company. As you can see on this slide, there are many of CEOs, COOs, and presidents and high-level managers, and this was our research sample. First questions, what is the awareness level concerning the Industry 4.0 technologies and sustainability practices in the company? And on the left, we can see the Industry 4.0, and on the right, sustainability development practices. And from this graph, we can see that in printing and packaging companies, the sustainability practices are mostly known better than the Industry 4.0 technologies, because it's related to the practical experience and the requirements. Because big brand owners in the FMCG industry require a lot of sustainable activities from these companies, printing and packaging companies. So that's commonly known that practical experience in this sector is very well known. And in the case of Industry 4.0 technologies, we can see that there is a little bit less practical experience about the Industry 4.0 technologies. And from this graph shows that which technologies are commonly used currently and in the future in the companies, printing and packaging companies. So we can see that Internet of Things, cloud computing, system integration are commonly used now currently, and also cybersecurity, and autonomous robots and additive manufacturing will be may be implemented in the future. On this graph, we set a research question: which sustainability practices are currently used in a company, or they are planned to implement in the future. So we can see that mostly nowadays printing and packaging companies focus on environmental pollution and management, or sustainable technology, or green sustainable product lifecycle analysis. And these are the main sustainable development practices commonly used currently. And these two graphs show some obstacles and hurdles which encountered during implementing in Industry 4.0 technologies in the printing and packaging companies from our first research, and as well sustainability practices. So the main of them are high investment expenditures and some deficiencies in existing infrastructure, as well as technical difficulties. And the next research question, do Industry 4.0 technologies and sustainability practices currently contribute to a company, or they will in the future? So we can see easily that in printing and packaging companies, we can see that they are strongly agree that Industry 4.0 technologies and sustainability practices are contribute and it's fulfilled to the company's success. Now I would like to invite Aldona for the extended research for the printing industry.
Thank you. Hello everyone. I want to show the extended research for printing company. We employed two kinds of participant sampling technique for conducting the survey and interview. The first technique for quantitative surveys examined 300 companies, of which 150 represented by printing companies and 150 represented by packaging companies. companies with up to 49% person employed, accounting for 90% of respondents, 10% of respondents of enterprises were companies with 50% and more employed. And the distribution of companies was performed and presented into a cohort. And the second sampling technique for individual in-depth interview consisted of 9 experts from industrial area representing sustainability, research and Industry 4.0 specialists. We addressed the following research question: how the SDGs, social development goals, can be aligned with selected Industry 4.0 components for printing companies, just to align or just to shift from traditional business model to a transformative business model. What kind of relationship exists between SDGs and the components of Industry 4.0 at present? And what is a digital business model for printing companies in terms of addressing sustainable development goals supported by components of Industry 4.0? The study started with recognizing the knowledge of Industry 4.0 and sustainable development goals among the companies, among the respondents. And from the slide, we see that 86% of respondents didn't know what the technology of Industry 4.0 is. From the 300 surveyed companies, only 18% did something about sustainable goals, which are promoting by the United Nations. Selected results from the first interview show the implementation status of Industry 4.0 across addressing sustainable development. So the results show the status in terms of SEs, technologies which are already implemented and to be implemented in the future in the printing and packaging companies. Cybersecurity. This is the most used component of Industry 4.0 today. Almost half of companies declare to use this technology. System, the next one. System integration is being implemented among 26% of Polish printing and packaging companies. Why? Simulation system component with 23% of respondents. 6% of surveyed companies declare the implementation of the system integration at the present, and only 3% are implemented other technologies like simulation, cybersecurity, and IoT. Augmented reality and autonomous robots are very rarely used. Among the companies, and other components used by companies which intend to implement within 1 year or more, several years, additive manufacturing dominates. Further research what happened? This is the picture without bars, but I see the bars on my screen. I don't know what happened. So I wanted, in this research, I wanted to show the next question which responder ask how the SDGs, 17 SDGs, social development goals, influence the planning business model in their companies. And it's hard to say, but the 50% of respondents declare that the decent work, this is the decent work, SDG 8, and economic growth as most important. Then followed by climate change, climate action, 53%. This is the next one. 13 SDGs, and the gender equation with value of 51%. Slightly fewer, there is indicate clean water and sanitation with the value of 49%. Something goes wrong. Then the SDGs 2, 14 and 15, zero hunger and life below water, life on land, will likely have lower impact on the planning business model when we compare with other sustainable development goals. The second interview were carried out with expert group which included 9 industrial experts representing research area related to sustainability and Industry 4.0 components. In this research, alignment degree of Industry 4.0 with individual sustainable development goal were investigated based on the scale use from -3 to +3, where -3 means strong negative alignment and +3 strong positive alignment. After analysis performed, we can distinguish 5 social development goals based on the Pareto rule. And there are SDG 3, good health and well-being, SDG 8, decent work and economic growth, SDG 9, industry, innovation and infrastructure, SDG 17, partnership, and 12, responsible consumption and production. The highest, when we see on the next figure, we can see that the highest value was achieved for cybersecurity in terms of sustainable development goals, represented by industry, innovation and infrastructure, followed by cloud computing and system integration, as well as big data with the same value 20. The lowest value for the same SDG 9, this is the industry, innovation, infrastructure, belong to augmented reality, only 5 points. Addressing the next SDGs, the responsible consumption and production, the companies can maintain the alignment with system integration, follow it the simulation and the autonomous robots, 15 points. In contrast, additive manufacturing represent the alignment, low alignment with value of 4 with the SDGs. And finally, for SDG 8, decent work, economic growth, the greatest value for the alignment was achieved by big data, followed by cybersecurity and the IoT. Finally, based on the field research resulted for 2 interviews, business model was developed for printing companies. The model considers 3 main sustainable goals. There is SDG 9, SDG 12, and SDG 8. Decent work and economic growth in the context of implementation of internal procedure for protection, for labor protection at work. The next one, SDG 9, industry, innovation and infrastructure in the context of sustainable implementation, industrialization. And last one, SDG 12, responsible consumption and production in the context of sustainable management and efficient use of resources, natural resources, and adoption of sustainable practices. The result also reveal that the value proposition in the middle of the canvas of the model identify industry 4.0 components such as additive, big data, additive manufacturing, cloud computing, IoT, cybersecurity system integration in meeting the mentioned goals 8, 9 and 12. Cybersecurity is most listed directly across all canvas, influencing the whole supply chain in the printing industry, both internal and external. What more? Big data. Technology support order processing, market and also supply analysis, affecting key partners canvas, key attributes and customer relationship. Such technologies may influence other canvas, the value proposition and the revenue streams if companies are advancing in the use of such technologies. The same perception, but for order processing, is cloud computing. System integration also supports all business elements in this model in the context of processing, order processing. Thank you.
Thank you very much. Aldona, please stay with us. Maybe we have very quick 1-2 questions, because I know that all of you waiting for a coffee. But 1-2 questions, please. We have question? Okay.
Hello, my name is Agnieszka Kozyra. I'm a student of this faculty, and I have a question about the questions from the survey, from the research you did from the first part of the presentation. There was a question about awareness of Industry 4.0 technologies and sustainable practices, and the awareness of Industry 4.0 technologies were very low, and I was wondering if it is because those sustainable practices were already introduced to Industry 5.0 in those companies you have researched, or maybe they are Industry 3.0.
Thank you very much for the question. I am more than sure that my friends will answer.
Yes, thank you. This question was addressed to me, so I will answer. Of course, the Industry 4.0 and my colleague Aldona has shown us the extended research that over 80% of respondents from printing and packaging industry in Poland don't really know what are technologies of Industry 4.0. So, and also, of course, what I can say that many times I used to say that even we don't use every technology, every possibilities of from third industrial revolution, and what about fourth? Yeah, so and especially in printing industry, because many processes are offline, so and we don't use these possibilities. And of course, the educational role of universities, of knowledge institutes are essential for this, to increase the knowledge about these technologies, but not only. So, thank you for this question.
Thank you very much. One more question, maybe. Okay.
Thank you. Jan Rusiecki, DKR Consulting. Thank you very much for a very interesting presentation. Short question. On the slide where you shown the awareness of Industry 4.0, and on this second chart, the awareness of UN Sustainable Development Goals, what is the overlap of companies that are aware of both Industry 4.0 and UN SDGs? Did you measure that?
Yes, of course, they are correspond each other, and to find the relationship between the technologies of Industry 4.0, maybe also approach of Industry 5.0, for the sustainability development goals or sustainability practices, we wanted to search such and build a model, because we know that many of these technologies, there are based 9, but of course some literatures shows the extended number of technologies, and these technologies works and can, we divided in our 2 papers that they are correspond and they are helpful to implement many sustainable practices. Yes, thank you. Also, sorry Krzysztof, you can see again this QR code. Please try to use it, and you are welcome.
Thank you very much. I also invite you to, of course, participate. So I think we can go to the coffee, so we deserved for that. So the coffee room is the same like yesterday, so 341 in the 3rd floor. So we will meet after 20 minutes. So of course, please stay with us, because it will be still very interesting presentations. And on the end, I must be proud, because this quantitative research was funded by NAVA, so this is also, I think, very good initiative to point out. Thank you very much, and we can go to the coffee. quite big delay. So the presentation, I think, will be very, very interesting and, of course, related with our faculty, also researchers. So Mr. Piotr Szulewski and the team will present the speech. So the floor is yours, so please.
Okay, thank you for microphone. Good afternoon, ladies and gentlemen. I would like to introduce me. I'm Piotr Szulewski from Warsaw University of Technology, from this faculty, of course, and more precisely from Institute of Production Engineering. The conference is coming to end, so I suppose that most of important information about the Industry 4.0 idea has already been perfectly said, or at least mentioned. When we talk about the Industry 4.0 concept, we usually mean fully automated, modern, fully automated manufacturing environments. In my opinion, it's impressive, but however, it's a big simplification. Why? It's not a reality. It's not the truth. Please look at this picture presented on the screen. On the left side, we have an example of a traditional historic manual workshop. On the right picture, the totally automated environment is presented. It comes from Siemens company. I think that a reality, that the truth is somewhere in the middle. I would like to show you a few examples of actions taken by our team to implement support for real small and medium enterprises. The main goal of our work is to facilitate the adoption of small manufacturing enterprises to the demands of the modern automation. Okay. On this picture, yes, it's working. I would like to introduce co-writers of this presentation and work which had been done. Don't laugh at this moment. I'm everywhere. This is our team. Probably some people knows the person presented on this screen. Okay, time is money, so let's start the presentation. I told about money, so as an introduction to this presentation, few words about economy. This is the true observation, well known all over the world, that micro and small enterprises create the true strength of the economy. These kind of companies, in fact, that are most flexible, show quick reaction on changes on the market, so the reaction time is very, very short. They can survive in any problems. So it's really, really important for global economy. How to define these enterprises? In Poland, we have simple rules. First of all, the micro enterprise employs no more than 10 employees. And it's important, the annual net turnover should not exceed the 2 million euros. On the opposite side, we have a mini enterprise. Employs no more than 50 workers, and the annual net turnover should not exceed 10 million euros. From the statistical point of view, we have in Poland about 200,000 really manufacturing enterprises. It's a real power. The most important is that these companies, these micro companies, micro enterprises, work about more than 30% of the gross domestic product. It's a very large amount of money. It's a real economic power. In fact, such a structure I'm talking about is very similar to every developed economy in Europe, and some conclusion coming from this presentation can be generally applied. I told about money. Small and medium-sized enterprises are the most dynamic part of the national economy. In our opinion, there is no other option. We have to support their transformation into the Industry 4.0. This supporting is, in our opinion, of course, is a strategic action. No other way. On the left side of the slide, you can find a fully automated environment. The right side of the slide presents more real workshop. How to combine each other? It's not an easy way. To support traditional workshop, it's necessary to develop specialized solution, means hardware and software. For each real workshop, it should be prepared separately. There is no universal solution. The diversity between these environments are so great, there is no universal solution. We should focus on the details. Ladies and gentlemen, small manufacturing enterprises. What features are most intensive are most important for small manufacturing enterprises. It's possible, in our opinion, to indicate some recommendations of basic functional features. Accordingly, let's look at this slide. First of all, everything should be simple. Simplicity is the goal. It's very important. We should use popular, well-known standards, versatility, scalability, easy configuration. All components, software and hardware, should be as cheap as possible. It's very, very important because the small manufacturings usually, I know from my experience, have no enough money. So everything should be cheap. Please note that in various automation, we have a various automation environment in small manufacturing enterprises. And problems to solve are very sophisticated and complicated. We should focus on these problems to solve it. I would like to show you some examples of our work done for small manufacturing enterprises. First of all, time is money. The source of correct time is very important in all reporting activities. Professional timing patterns, for example, on the part of this slide, these professional timing patterns are usually very expensive and not always easy to access, especially if our internet network should be protected, and in my opinion, usually the internet access is prohibited. We have made a budget version of Time Server using a normal, free of charge DCF77. It's a radio-controlled service. It's free of charge. It's working stable, for example, for our watches. So it's a very, very good, cheap, and easy to access implementation. The correct time is distributed within the company network and using the Ethernet standard, and could be, for example, displayed on a public monitor. All controllers, all equipment, manufacturing equipment is synchronized using our time server. It's very important to synchronize all activities done in our workshop. Okay, next. This example relates to the popular ASE standard industrial network. This network is simple and rather inexpensive, simple and popular in Poland. In our laboratory, we use this network, to monitor the working time of different machine tools. We have developed specialized software to allow us to publish the data coming from our machine tools to the internet. We can use different hardware. Please find, we are able to use like a hardware controlling this network system. We can use a specialized ASI master card, a PC card, PLC, etc. So it's very, very universal solution. The most important thing is to concentrate on security. At the bottom part of the slide, you can find many solutions we import to our software to protect this information, to protect this data from unauthorized access. Okay, next. This slide relates to the distributed wireless temperature measurement system. It's especially established for collecting technological data. We use popular hardware and free-of-charge software to prepare this solution. Acquired temperature data can be collected in a local database or published in the internet as you like. It's a very simple, very useful construction. I would like to pay your attention that that's only an example that we are working with temperature data. We can use any data, any technological data. It doesn't matter which one. Okay. The next example shows the remote control and simulation. This conception is a simple robot remote control of simulation. This robot you can find on the right side of this slide. The full communication using internet, over internet, is established with this manipulator or a robot. We use a popular browser to control this robot. A popular browser, web browser like Internet Explorer, Firefox or Google, it doesn't matter which one. We also tested this solution with different operating systems like Windows, very popular, or by Unix. It doesn't matter which one. It's working in every kind of operating system. No problem with expansion or adaptation. We can use this construction, for example, to work with also professional robots. You can find that we prepare it to work with a very old standard. We can work with controllers which working with very, very old standard. It's a serial interface RC23232C, so it's a very universal solution. Okay, this is an example of simple and very, very inexpensive SCADA system, SCADA environment. It's used for controlling of the mobile manipulator. On the right side you can find it. The robot controller is a normal, standard, traditional PLC. Of course, this solution can also be adopted to work with more professional robots or manipulators. Okay, at this moment I would like to pass the microphone to my colleagues, but stay here, I will be back.
Thank you very much. I will show the project we did with some companies, not only SMEs, because Piotr says about gathering data from the machines, from the environment. So it is not so obvious to go to laboratory. When you go to the laboratory, you can use sensors, you can have access to PLC and gather information what do you want. But if you go to the company, they will tell you, for example, we have guarantee for this machine. You cannot open it and take the signals, what do you want. Sometimes when we make some projects, we cannot add this sensor, external sensor. We can use internal sensor when manufacturer sold machine with sensor, but we cannot add our sensor. So it is not so obvious to monitor some work of the machine. Here is an example of toolware monitoring system. We did in two projects, Aeronet and InnoGear. So we create a measurement system. We add external sensors, force sensor, accelerometer and acoustic emission sensor. It was similar as Professor Teti said in the morning. And we, in this project, we cooperated with Pratt & Whitney. So this is a manufacturer of Boeing airplanes. So it was not so easy to get to the factory and said, give us a machine, we want to install some sensors and take the signals, and we will build a system for toolware monitoring. In the second project, they select the machine and they said, we will refurbish this machine, we will replace the PLC in the machine for a new, and we will program procedure to send signals for you. So if the machine is quite new, if we don't buy from manufacturers some extending card, we can communicate with the machine. In many situations, there is no possibility to connect to the machine. Even if we prepare some hardware or software to communicate with the machine, in not every case we can communicate with the machine. So in that situation, we get from the machine not only, because in the first project we get some basic information, start of the machine, start of the feed of the machine, but that was digital signal taken from relays. It was one machine working, 0 machine is not working. It was in the first project. In the second project, when we can join with the refurbishment of the machine, we get the information like the feed speed of the machine, not only start, but localization of the tool, X and Y, position of the tool, and speed of the tool, speed of rotation of spindle. So different space when you get can get all the information from the machine. In the second project, because Pratt & Whitney is not SME. SME was in Ireland. We did a project called Realism for the Ireland. Also Professor Tetti from Naples did the similar installation in his contact in Naples. And the third installation was made in Norway. So we create a monitoring system also connected with PLC, but on standard when we communicate through the relays with the machine. Also the simple signals type start of the machine, start of the feed, but it was enough to run this toolware monitoring system. There was also a problem because this company in Ireland, it was manufacturer of the medicine, some tools like tweezers and others. They had quite new machine, and we tried do some extensive cards to the control system to the machine. And they also said, we have warranty on this machine, we cannot get inside. And the support then didn't have buy the extensions on warranty. They couldn't add any extension to the PLC to the machine. But the internal programmers did some job, and they gave us some digital signals through the relays, like start of the machine, stop of the machine. So it is not so obvious to communicate additional monitoring system to the machine, but we didn't. We can do such kind of job. So it is very interesting. So if you planning the project like this, we can cooperate, because we like job like this. We have a lot of contact with Berghoff, with Siemens. We're trying to communicate with these companies because there are PLCs that are used in the machines. So we tried to create some type of standards we can use in communicate with additional system, because in Industry 4.0 it is also important not only analyze signals offline. We measure some signals from sensors, we can send to the cloud, analyze in the cloud, and when the information will back to the machine, the information can be old. It is important to have some real-time systems. So we can program real-time monitoring system. It must be edge computing near to the machine. We can send to the cloud and of the analysis. We can say how fast we change the tools for the new, because our system detects how the tool is worn, when there was, and how frequently there was a catastrophic tool failure, it is important for manufacturer, for the company. But the calculation must be close to the machine because there is real-time calculation. Okay, thank you very much.
Coming back, thanks. As Mirek said, the communication is the key. It's very, very important. It's a real problem when we try to solve problems in a normal factory. Guarantee that's a problem. Okay, coming back, concluding this presentation. You have seen some examples. We presented our activities for small manufacturing enterprises. I would like to take this opportunity to say a few words, just to add a few words about engineering and scientific knowledge and our competences. These are our competences. You can find it on the screen. Automation, communication, vibration, diagnostics, analysis, control, machine construction. In fact, all these competences coming to the smart factory, but we all think about smart factory, not a large company, but smart factory as a small manufacturing enterprise. If you find useful this information or you would like to cooperate with us, you are welcome. It's difficult to include all aspects of the problem in such a short presentation. We hope we were able to present our point of view and prove that it's possible to make a specialized software and hardware useful for small manufacturing enterprises without competence of a large, big company. We use only popular standards. It's very, very important because all our solutions are rather cheap. It's important for small manufacturing. Of course, we are not real competitors for large companies, but we'll try to solve some real, maybe small problems. All our projects were really tailored. Okay. Please look at this picture. It's a well-known motto made by Henry Ford. Meeting together is a beginning. Sticking together is a progress, and working together is a success. We think that it's a very, very good motto, especially for this time we are living now. What will be in future? Nobody knows. We know. Only this person who knows the future can make a good, right decision and become a true winner. It's very difficult to predict the future. Let's make an experiment. What future brings? In our opinion, the future factory will have only 2 workers, 2 employees. Only 2, just 2. First will be the man, or according to political correctness, human. It will be a human. The next, that's a question. The next worker will be a dog. Why? It's important. First of all, man, human, will be there to feed the dog. That's a normal situation. What is about dog? The dog will watch human not to touch anything in fully automated machines. It's very, very important. Of course, I think that, it will not be true that our future will be a little bit better. Why? We should concentrate on a text. Always look on the bright side of the life. It's a very, very popular song from Monty Python. It's a good idea and good motto. Okay, that's it. Thank you for your kind attention and have a good day. That's all. Thank you.
Okay, thank you very much for your very interesting presentation and very nice summary. Maybe we have some questions, so please don't running up. So we have some questions to Piotr. Yes, of course, I'm more than sure that, but maybe we have some comment, question. Yes, we have. Okay. Yes, we want to ask about something or comment or not? No? So we must find some question, come on. No? Yes. Yeah, so they are shy and they are still ask difficult questions. But okay, thank you very much. It was very interesting and inspiring, and I think you also are happy with that. So the next speaker will be Jaclyn Varver from Technic company. He presented also yesterday, as we remember, and today he will bring you more interesting applications of Industry 4.0 solution in the practical ground. So please, Jacek.
Okay, thank you. Good morning, everyone. After this short presentation, I would like to talk a little bit about our case, implementation of cloud of AI platform in our company. You are working in electrical equipment industry. This activity is realized as a part big project. It's a kit for SME. About this project, it was yesterday presentation. We work together with our partners because we are pilot, one of the 4 pilots in this project. Our coach is a Faculty of Mechanical and Industrial Engineering. It's colleagues from Warsaw University of Technology, and our technology provider is a GINCO Analytics. I would like to say a little bit about challenges, milestones and problems in this project. Short agenda, it's a short presentation about Technic. It's repeated from the yesterday. Process characteristic, defining the problems, suggested solution, result achieved, summary and conclusion. This is the same presentation from yesterday. We are battery designer and producer. We have 30 years of experience in this market. We have 260 employers. We have large R&D department. It's 30 engineers, quite large turnover, and now 2 plants in the near on the Warsaw in the Piaseczno. Okay, few words about current process. First step, it's cobots. It have been starting yesterday, if you remember. After the cobots, we have assembled cells in the cell holders. It's a module. And the next step, it's welding. Of course, between these 2 steps, we have to put the tabs for welding. Next step, it's a final battery module after welding process. Finisher battery module, it's assembled from 2 battery modules, single battery modules. And this finished battery module is used to build battery systems. For example, in this battery system is used 10 finished battery modules. It's more than 2,000 cells and more to 8,000 welding points. And this is, for example, this battery system is used for excavators. And from this process, of course, we have internal check welder. It's an internal part of welding machine. And when something wrong happens during a process, this is a weld point is wrong, have wrong quality, machine is stopped and waiting for decision for operator. Usually this welding point is repeated by machine, and this is a source problems when we see in the next presentation during a methodology of analysis of data from this process, because each repeated welding, it's a next row on the data. And from each cells, usually we have 4 rows of data. And when sometimes some weld is repeated, we have 5 rows of data. It's a 5 points of welded. Some overview of requirements. Of course, first, it's a more precise evaluation of the quality of the welds, faster machine data analysis, operator support in the making decision, predicting the possibility of an error. For example, it's a contamination of the electrodes, improve operator comfort, some human-machine interface. It should be friendly for operator. Product quality improvement, reducing the number of scraps, less downtime of the machine due to electrode replacement or cleaning. Of course, improvement of operator knowledge of process, also specialist, and support for KPI implementation. This is a functional diagram how this status as is. First is a welding machine. On this welding machine, we have dedicated machine computer. It's a part of the machine. On this computer, we have dedicated application. It's working as some SPC tools. There are some analysis about process. We have second way of analyze this data. We can take this data manually. For this is needed embedded data description application. And after this process, we have TXT file. And we can take it from this computer and analyze it somewhere offline on our offices. Of course, everything is happen, post factum. We analyze data, we analyze process which happened few hours, maybe few days before. And the current analytic method seems ineffective. It is necessary to implement solution extending the existing analytical methods supporting the decision-making process. And it seems that we should implementation some modern way of analysis of data. We choose some AI application, AI solution based of the clouds. This is some proposed solution. It's open source AI platform. It's a part, of course, Kit for SME project. It's built. This platform is built during this project. Of course, for good working of this platform, we need good data and good tools and good methods of analyze this data. This is a current situation. This is a welding machine. Of course, it's a computer which is part of this welding machine. It's a database. It's on this computer. From this computer, we will send data to the AI platform. This AI platform will be sent back to information from operator that this process is okay, this welding point is okay. If not, operator should have information about it rapidly from the real time. Of course, we can take from this platform data and analyze it offline and working from some optimization on this process. But unfortunately, it doesn't work that because we meet one problem. It's a first large problem during this project, because data from this welding machine have a little bit strange format. It's a FS format. It's some kind of manufacturer file. It's created by a manufacturer of welding machine. This file, this data needs to manual decoding by dedicated application. This application is a part of welding machine, and this is not possible to automate this process. It's happen online, and there are no possibility to read process data by the platform. In there you see example from this software data, and we looking for solution how to decoding, translate this data from some reading from platform data. And first idea it was some kind of online string conversion test on a source file. It was very difficult. Second idea, it was use some macro. It's an AutoHotkey, it's an application. This macro should run this dedicated application to translate this data from this strange format to, for example, TXT format. Third idea, it was buy from a welding machine, dedicated machine manufacturer external description device. And fourth idea, it was prepared from my colleagues from VAM Technic, signal interpreter. And finally, we choose this idea. How it's work? We see a welding machine. We develop, our engineers develop description scripts, and we connection this description script directly from the power unit of welding machine. We can say it's like some kind of PLC, something like that. This description script take data directly from the welding machine, from this unit, translate it to the different format, send to the computer. It's a part of welding machine. I'm sorry, and translate to this format. It's a JSON format, and this is a send from to the AI platform. And this is, in this way, we fix this problem with the non-standard format of data. But in SASFU and predictive quality of the model, additional analytics of machine input data required. And this is a very difficult part of this presentation. And this is a part about analytic this data. In first, if I mentioned about this problem on the beginning of the presentation, but when welding machine repeat some welding points, we have additional row of data, and this was problem when we try to analyze it in the, how to say, standard form. We, our partner Ginkgo Analytics prepared this graph, use this model to create these graphs, and we see wrong and good welding points. It's overlap. It's a completely overlap, and this strong overlap between good and bad points. And on this confusion matrix, you see a large number on the false negatives that were in fact negative were classified as a positive. And this is, how to say, I don't know how to translate, ślepa uliczka. Oh, yeah. And our partners, Ginko, find to some solution, and he finds some iForest methodology, and they use this methodology to analyze this data. After that, we achieve this kind of graph. You see that this, we hope, wrong points, it's only for few idea, it's not few area, it's not overlap as previous methods of analyze. Conclusion and future steps. Current methods would seems to be a good way to achieve satisfactory modeling quality and consequently support to the process in the terms of predictive the quality of welds. Next step will be work with Ginko to select a methodology for fusion data analytics, work on welding data. It's unfortunately manual work. Test of the application covering data from welding machine, because we develop it, but it's still testing it, and connection to the kit for SME platform, and work on results. Thank you for your attention.
Thank you very much, Jacek. Do we have some questions to our speaker? So please come on, you have opportunity to ask guests from industry. So no one want to ask about something? Okay, if not, so thank you very much once again, Jacek. And the next presentation will be also quite interesting in a different field, in the supply chain management. So the speaker will be from Bosnia and Herzegovina. So Miroslav, please come and present your presentation. Okay. Okay. So the floor is yours. So our foraging guest.
Thank you. First, I would like to thank the organizer for the invitation. It is a great pleasure to be here. I'm coming from Bosnia and Herzegovina. It's a country in transition to European Union. I will try to explain some aspects of business and small medium enterprises in my country. Typical small medium enterprises in Bosnia and Herzegovina is family-owned companies, where owner of companies acts as the general manager also. There are no clearly specific sectors in company, and existing sectors have a multifunctional role. Our companies have problem with resource, especially with financial resource, supply sources, and last 5 years with human resource, normally young people going to West countries, so we need additional human resource. Company focused on local or regional market, depends of small customers, or strategically focused on a large company, exactly large company from West Europe countries, Germany, Italy, Austria, Slovenia, an example. The procedure is very simple, working procedure in this company. Formal rules, they are simple and fast internal communication, but this company is very flexible. It's way to be more flexible than large companies. If you're talking about information communication technology, typical is small medium enterprises in Bosnia and Herzegovina use technical tools like CAD tools, CAM tools, on example, but generally using modern ICT solution is low level. Some solution like enterprise resource planning is too expensive for our small medium company. It's problem. This solution is too expensive. It's complicated to implementing in company because no resource, human resource or procedures. Also, we have a situation that companies only basic records about our business stored in digital forms. Usually with accounting information on example. They're not changing information between company and clients and customers in digital form except email. One small medium company is one link in global chain, supply chain, very connected with the suppliers from one side and on the other side with our customers. COVID pandemic disturbed global supply chain. And in this situation, small medium enterprises is a subordinate position to large company. We have company who works with a large company from Germany, Italy. We are in subordinate position. We have a subordinate role in this supply chain. So flexibility of our company is become a significant feature for all companies. But all company must be efficiency, effectiveness, and flexibility. It's a frame for measuring business performance in small medium enterprise. This frame is strongly connected with the supply chain structure and with supply chain management. Two approach to rising flexibility of company. It's a proactive approach like component unification, risk sharing, outsourcing, reducing of lead time, making flexible contracts, or a reactive approach, for example, safety stock, extra capacity, supplier diversification, and something else. I will show our works. I'm working with the company. I have good cooperation with the companies from metal and the textile sector in Bosnia and Herzegovina. Over 20 years, I strongly connected with these companies. I try to involve simulation in this company, especially in the small company where it's problem. We developed a system, simulation model, system dynamics techniques, continuously simulation. It's big model with 4 modules. Each module is each module is separated, has own rules, has own measurement, own prediction example, and its models connected. I can explain some models. It's module M3, preparation and execution of production process. This model monitoring process, work process from launching works to final product entering. This module connected with the other 2 modules, salary and inventory management. From module 2 give orders, customer orders, and from module 4 we have information about stock availability, for example. It's possible to set big number of parameters of model. On example, number of machines, time for preparation, working time, stocks. We can set delays and breakout of machinery and some other parameters. Module M4, sorry. Sorry for my bad English. Speaking better English last night. All you know about speaking. Inventory management, monitoring inventory management in company. We have monitoring inventory of raw materials. We can set different politics of management, inventory management. For example, we have flows, materials, and process procurement or raw materials. Finally, after finishing simulation, we need analysis of process. So its frame, it's part of model, frame of business performance. That it's big number of performance. So we need in the flexible performance. It's very important for our company. Only business performance is not enough for our company. We developed own programs for this simulation. Systems dynamics is not new techniques of simulation. It's no simulation. Also, there are many softwares for this type of simulation, but problem is difficult. We need a big number of information, big number of parameters in our simulation, and very important, we need strongly connected with the information system, on example. So we developed our own program in program developed in Visual Basic. This program help customer to set up parameters of process simulation and other parameters like number of machine, material requirements, processing time, prediction, on example, prediction of customer requirements, and we can automatically equation of performance measures also. Its part forms from this program. In case study, we have example using programs for simulation in very small company. It's company with only 28 workers, including management workers. Company produce wide production program. For small company, it's very wide production program, but they have a standard standard products produced by stock for stock, and we have make the stock system to fulfillment of requirements of customer, and also company produce products with customer requirements and make it after requirement of after order of customer. We need for basic experiment about 10 proizots and about 50 different materials. We set up a program according database. This company have implemented the information system more than 20 years. They has information system, and we full integrated program for simulation in integrated system. So it's not problem to implement process of simulation. We simulated in this experiment period of a quarter of year with simulation step only 1 working hour. Result of experiment performed by our program. You can use level inventory by different raw materials. On example, we have also schedule plan. We have monitoring level of finished products or products in working state, and finally automatically equation of business and flexibility performance. It's very important for us. Now we can try to improve performance of companies. We can see low level, on example, we can see a low level of fulfillment orders for existing stock or timelines of delivery. In goal to increase this performance, we can try make some parameters of model or parameters of company. In this experiment, we increase capacity. Adding a new machine in model parameters, we increasing capacity, and we increase many of performance of company. Not increase exactly, but predict increasing of performance. But usually, if we something increase, other performance may be decrease. It's not. It's difficulty to only increase some performance and don't decrease other performance, and we can see we predict huge level of finished goods. So we need, in this case, additional storage buildings. It's not maybe good solution for small company because we increase by 100% level of finished goods. So we try combine different decision, different parameters, changing different parameters. So in next experiment, we reduce batch size to aim to low level of finished goods, finished products, for example, and allow program to simulate to real-time change working schedule, and we allow also material procurement for alternative source, because in previous experiment we have a lack of materials sometimes, and extension of delivery time with the customer contract, we predict additional delivery time. Simulation program predict good performance improvement. In this case, you can see green show significant improvement of significant improvement of performance without negative effects on prediction measures. I finished. Achieving flexibility becoming increasingly important for small medium enterprise. Simulation tools can significantly improve supply chain performances, small medium enterprise. But are small medium enterprise able to use these tools? It's difficult. On start, I say there are no resource, no in a small company like company I explained, there are no workers who specialists for mathematical analysis or specialized for simulation. But if you integrate a simulation process into other process in a small medium enterprise, you can make simulation easier to use in small and medium enterprises. Thank you for attention.
Great, thank you very much. Do we have some questions to our foraging guest? Okay, one question. So, Dr. Bartłomiej Ladysz.
Thank you very much. The question is about the tool you have used, because you said there are many software applications to support systems industrial dynamics. I was just wondering which is your preferred tool. I mean, me myself, I'm using AnyLogic software as a preferable tool, and the question is if you use that one or maybe Stella Architect or maybe something else.
Thank you, Bart. I used also software for simulation. It's many softwares on markets for simulation in system dynamics method also. I'm basically research based on software. An example diagram I show is also work my Dyne Systems software. But I'm a calculation engineer who working on develop the own ERP system implemented in many companies in Bosnia and Herzegovina. So for me, not problem to program and include this software, new software in existing software in company. Also, we have database connected to this system to connect we can connect with other information system also via database, an example.
Okay, thank you very much. I think in Thursday it will be a great opportunity to ask more questions because we have a very big delay. So thank you very much. And in the Thursday, our guest from Bosnia and Herzegovina will have a guest lecture. So I hope that you in Thursday. Wednesday, I'm really sorry. So in Wednesday, so tomorrow, our guest will have the guest lecture. So I hope that you received the invitation for this lecture. And one more thing I want to add. So I want to thank you for the Dean, Mrs. Joa Kryznowska, because this is our guest from the next NAVA project, CEPUS. So as you see, the NAVA support this international exchange from academic partners, so it's of course very, very nice initiative. Okay, and our last but not least speaker will be my friend from the WT, from our faculty, Jacek Kozlowski, and he will also present you very interesting topic. So Jacek, the floor is yours.
Tu jest drugi. Nie.
Good afternoon, everybody. It's a great pleasure to be here. My presentation, as Chris said, is last, but I hope that fortunately will be not least. I have something new. It's difficult because I thought that everything was said, but fortunately not everything. So that's why I would like to share with you with my current experiences and my current researches, which are focusing near the virtual expert, which can be used as a support in the issues of predictive maintenance and predictive quality. It will be related to the casting processes. Agenda is very short and simple, introducing methodology. I will show you two problems which will be analyzed. I will show the solutions as a proposal, next steps, and conclusions. Okay, if we will take an approach that the process is described as a high-pressure die casting machine, and we have, like it was said, mentioned in the previous presentation, existing embedded data acquisition system. If not everything can be acquired, collected as data, we can, of course, create parallel data acquisition. And we have some other sources, external data sources, for example, weather from the internet, existing management systems, ERP, existing analytical tools, computer-aided engineering, or Excel analytical tools and their results, and human sensing, for example. Everything can be collected in the database, but before it, we have also process control. Process control, which can be focused near the quality and direct control of the process with the engineering and statistical approach. So database, it's also should be also, of course, available external or as an external hybrid internal solution, but the data should be pre-processed in the data preparation process. Yes. So if we have this sequence of activities and tool solution, we can start with using any computational engine. It can be AI, deep learning, big data, machine learning, computational intelligence, data mining. I don't want to discuss about this names and about these shortcuts because it's very fuzzy. Generally, I'm using neural networks, decision trees, statistics model, and sometimes even hard rules. And what can we achieve? How can we use the computational engine? We can use it as a predictive system. We can use it as a knowledge extraction system and control systems, as also additionally as a visualization and reporting tools and solutions. We have also few internal groups of client suppliers as maintenance department, R&D department, new product development department, technology department, as also operators. And if we add some data transfer solution, it is almost I40, of course, not exactly. Okay, so the groups which can use the predictive maintenance are all of them, and additionally science, like I am, for example, we are. The same for the knowledge extraction system. Control system can be used directly to the control steering the machine, or indirectly as support for the, for example, operator for 0, which was mentioned today. And what is knowledge extraction system, in my opinion? It's not directly my opinion, and I tried to find the definition in the literature, and I think that these two sentences, the process of gathering and analyzing significant volumes of data and compiling it into useful information, and extended with that can be processed and understood by a human expert due to its volume, diversity, and complexity, I think that it can be treated as a full definition of knowledge extraction system. And as a part of the knowledge extraction system, of one of the solutions can be virtual expert. Virtual expert is a name which is not so easy to find in the literature. More popular are virtual assistant, which works, which can be as a set of hard rules that supports human activities. Virtual agents, very popular, that imitates humans' behavior, especially used as in the conversation systems. And virtual expert definition is formulated by me, based on my experience, as a set of external queries created by a human expert to intelligently interrogate AI, yes, and extract knowledge from artificial intelligence models. And it is very significant, the last part of the sentence, rejecting the concept of social relationships and user iterations. I want to forget about this. It should be only a kind of calculator. And the model of working of virtual experts is very easy. The first step, of course, it's creating, selecting the mathematical model, even hard rule. It doesn't matter what is the source of calculation and source of knowledge with the learning database. And the third step is one of the most difficult, because we have to prepare interrogation database, which is called by me as an interrogation strategy, which will be used during the interrogation process, yes, and the achieved answers based on interrogation database during the interrogation process should be analyzed in the inferencing process or something like that, yes? So these 5 steps, creating a visual expert. And I would like to show you one of the examples which is realizing with my students on my classes, modeling of manufacturing processes, how this virtual expert works, yes? So the question is, what are the most significant process parameters, yes? It's very simple, interrogating, but of course we have to have an idea how to interrogate the model. So if we decide to analyze the process parameter 1 in this example, and we decided to set the values of this process on this parameter on the minimum, maximum, and average. It's this ranges or these values can be from the learning database, for example. We created as many as we want a number of samples, and in each sample, the rest of the parameters was stayed on the constant level, defined on the constant level. Yes, so we can calculate with using interrogation the output, so the prediction for each sample. So it means that if the rest parameters are on the constant level and only one parameter is changing from the minimum to the average to maximum, then we will achieve the different, or should achieve different output predictions, which will be related only to the changing of the analyzed parameter. And finally, we can calculate what is the difference, dispersion, delta for each sample, and maximum dispersion can be an answer. So finally, we can achieve the result that, for example, process parameters has 4%, process parameter 2 11, and process parameter 3 7% of significance. For example, in relation to the range of changes for all 3 parameters. Yes, all 3 parameters is 100%, so single parameters gives us visible. And it is a problem. It's a real problem because single parameters don't have significant influence to the process. We can do nothing, almost nothing, by changing only one parameter. So the question is there, or are there any methods to check what combination of process parameters affects the process more, or is the synergy between the analyzed parameters, process parameters? Yes, we should find if the synergy is. And now, following the rule, the learning by doing, I made a kind of analysis based on the Foundry data, which the source was from the high pressure die casting process. In typical process, high pressure die casting, we have above 100 parameters collected. And of course, if we have 150 parameters collected, the analysis of potential causes of quality problems or problems with the maintenance, any one problem, is very difficult because of the large scale of the analysis. So, okay, if we extrude the melting process, which is the only part, and we'll try to describe this process with the chemical composition, we have 11 alloying elements, chemical alloying elements, and we have relationships between this chemical composition and mechanical properties of aluminum casts, yes? And there is a necessity to select the most important, most significant groups of alloying elements that have the strongest influence of the hardness of casting aluminum. So that was considered to develop the tool who allows us to select the most significant process parameters. And that tool, as a pilot, as MVP version, was developed a few years ago in Excel file. Yes, the tool allows to analyze the manually selected significance group of signals. So, for example, in the visible example, if the human expert selected these parameters, we can observe that significance of these parameters is 0.8. In relation, that significance of all parameters is 1, so 100%. So, as we can see, these two parameters manually selected by the human expert, giving 80% of the whole range of changes of hardness of aluminum alloy. Very good information, because we don't have to be focused on the all parameters here, 11, but generally 150, but only on 3 of them. These 3 parameters can be also found very fast by using the bottom graph. It's an operational graph, because this graph shows the average significance of group in signals, so where the significance is maximized and number of signals is minimized. That was the first one group on this bottom graph. Everything based on the special custom techniques of AI interrogation and result analysis. If we want to be more precise, and we don't want to analyze the billions of combinations of signals, we can use the extensions of the first tool. So and answer the question, what are the most significant of groups of alloy chemical composition with simultaneously smallest amount element in this group? Yeah? So we have to find the groups with a small number of signals and high significance. And this tool has also its own implemented manually procedure. So if we have the group with the larger number of signal and combination of smaller number of them gives similar, based on the level of similarity, significance, then the larger group is removed from the analysis, and finally we are achieving the visible solution with the groups of signal, with the number of significance and number of signals in each group. So, for example, we can find out that first group with 2 signals, silicon and copper, got almost 60% of influence in relation to the all total 11 chemical composition parameters. So, finally, if you have these 3 parameters, we can try to find out what should be the level of these 3 parameters to achieve very high, above 100 Brinell hardness of aluminum alloy. So by using of this tool, by fixing the rest of parameters on the constant level and allowing to find out using optimization methods, for example, simulated annealing, we can very fast find the level, and as we can see, to have a high value on Brinell hardness for the aluminum alloys, all three parameters, aluminum, copper, and manganese, should be on the highest level. And another one problem, because this solution, which was shown during the first phase, will be worked properly if the prediction quality of our model, computational engine, will be satisfied. Yes, but it is a true and real problem, and in case of the prediction quality in preventive models. Preventive, so it means that we need to have a prediction in some declared time in advance. Yes. So the problem with the high pressure die casting process, which is realized in our friendly foundry, NEMAC foundry, is the forecast for the preventive activities to do not have downtimes should be planned 3-4 days before, about 100 hours. So that's why the models should be created which allow for such prediction. But unfortunately, the problem which is analyzed, for example, problem with the vacuum filter, do not have behavior like other processes in which bearings or other processes visible here, which can be defined, for example, based on vibration or noise level, that it's a tool where 20%, 50%, 80%, it's only exemplary manually written by me, but it is not so easy like here because there is no similar methods to analyze the vacuum filter behavior and to simply describe and predict in the future. That's why here is the exemplary database. Of course, only a part of database because we have over the 150 parameters and we have one record. And we have, for example, 4 days ago, this historical data, we have no good leakage status because each cast got leak test and leakage status is collected. So the question is, foundry requirements to have prediction of breakdowns or quality issues 100 hours, or about 3-4 days in advance to realize preventive activities during planned downtimes. So, of course, as I mentioned, this is not so easy with using classic techniques. It is not possible to predict based on this record and process parameters defined and as a result to predict something what will be 100 hours in advance if the cycle time is about 2 minutes. It is very difficult, almost impossible, and it was confirmed by our researchers. That's why the key idea, which was a result of our current researches, is using behavioral patterns. Behavioral patterns, so it means that we are not taking the single row, the single record for interrogating the model, but we would like to create a kind of behavioral description. The easiest one possible is, of course, the trend. And for example, using the trend as a behavioral pattern, depending on the resulting trend angle, for example, 45%, and we can change this part of data which is related to the time, longer time sample. For example, if the trend is increasing +1, constant or almost constant 0, and decreasing -1. Yeah? So it is these three values are a behavioral description, but it's a completely different approach. It's not related to the one record, but for the defined previously range of time. Yes. Another one approach which was analyzed up to now is more advanced. We are using statistical process control cards. And we are using Western electric rules or I forgotten the second, sorry about that, but general statistical process control rules as a Nelson rules, as a behavioral pattern. And depending on the most probable rule, so we are calculating probability to get one of the 8 rules, maybe a more number, we are seeing that, for example, rule number 3 is 80%. So it means that behavioral patterns, so the behavior of this analyzed data is closest to the rule, the Western Electric rule number 3. It will be an input to our model for the prediction, not single record, but the rule number, for example. And we had the first results of this approach. As you can see, these 3 days were analyzed with using decision tree model, classification trees. And for the 3 days ahead and using the pattern, behavioral pattern based on trend line, we achieved not so satisfying result. Maybe if we wanted to predict that nothing happened, we have 94%, it's acceptable. But one will be predicted with 76% of prediction of quality. So it's okay or not okay. Of course, even 5% saving of time of breakdowns is an advance in relation to now if we don't have nothing. For the SPC pattern, I had two, of course, results were shown. One day I had a prediction of failures or breakdowns, or 3 days should be. I had prediction of breakdowns. So 1 day ahead is very good prediction quality. As you can see, 95% of cases will be or can be predicted, and we can but only 1 day ahead. So if it will be enough time for the department to plan the preventive task, that's okay. A bit too large number, we have false positives. 26% cases where nothing happened will be shown from the model as that something happened as a suggestion, so it is not so good. And the results for the SPC 3 days ahead, the interesting is that 1 day ahead or 3 days ahead in prediction of not okay and okay cases are opposite side. So 3 days ahead, okay cases 92%, and not okay cases very good, 81% for 3 days ahead. So with the maintenance department is quite okay in my opinion. And the almost last slide, which is realized now as a master thesis project with my student, visible and available here with Mert. Danish, I do not write your name because you are making a bit different task. I will mention about you if I will show results of your work. My student, master thesis student, proposed to use Monte Carlo rules as a behavioral patterns depending on the most probable rule given a range of variables is converted to a rule number. For example, for the rule number. So these patterns have the shape defined in advance, and we will create the learning database. Then after that we will use the convolutional neural networks for pattern recognition on the first, and if our selected data range of data will be fitted to some of the pattern, yes, then it will be used as an input in classic machine learning method. So what are the conclusions? Virtual experts sounds to be a useful tool as a support decision. It can be created on the basis of all possible mathematical models. Even AX plus B can be used, even hard rule if then else can be used if this structure is difficult. Requires some knowledge on the stage of the preparation, the strategy for the artificial intelligence interrogating, yes, on this stage. And it seems to be safe to implement in context of concerns about human resources. So, and the possible necessity to implement procedures of adoption methodology. It should be created as a tool, as a calculator, not as something with which is the interaction with the user. Of course, it's possible to create universal tool with universal input settings, output, and then it will be possible to connect to this tool, to this virtual expert, with almost all, even with Excel analysis. And in relation to the second part, the behavioral patterns used for as input instead of the direct parameters for predicting a long-term phenomena, yes, seems to be effective and perspective, but I'm still working on this. Thank you for your attention.
Okay, thank you, Jacek, for the presentation. And do we have some quick question for our speaker? Really? Even single one? No? Okay, so thank you very much once again, and I hope that you will, of course, establish your cooperation with many other students and researchers, so thanks. And ladies and gentlemen, I want to very short summarize these 2 days of symposium. I know that you are starving and lunch is probably waiting for us, so I will try to be very fast. So I think we can skip the discussion part because I asked about the question after every presentation, so I think we can skip this agenda point. First of all, I want to apologize that the Dean Chmielewski will not summarize and make some speech on the end of this symposium, but he has now very important meeting with the rector of our university, so please forgive, of course, this, and I hope that you understand. So he asked me to summarize very shortly this, and of course, on the end, I want to close this symposium, but I will try to be very, very fast. Okay, so in these 2 days of the symposium, we have many great speakers. So we have 5 keynote speakers, so Professor Lucas da Silva, Professor Marco Macchi, Professor Rodolfo Haber, Professor Francesco Delisola, and Dr. Thomas Rupert. So of course I want a personal thank you very much for attending, and of course it was a really great pleasure to hear your speeches. But of course, among the speakers we have also many other distinguished guests. So we have CEOs of the companies, we have experts from the industries, we have consultants, and also we have many great researchers. Yes, so we have professors and doctors from our faculty and from different universities. So I'm really glad that we can go through the theory to the practice, and of course we have seen many interesting theoretical presentations and of course practical ones. So it's very good because in my opinion research should and even must meet the industry. So the bridge between universities and industries is quite high, especially in Poland. So I think we should reduce this gap and of course cooperate more strictly. We have during this symposium guests from the 6 countries, so from the Portugal, from the Italy, from the Spain, Hungary, Bosnia and Herzegovina, and we have also representatives of Beckhoff from Germany, and of course we have Polish speakers. So I think that we can say that it was really international symposium because 6 foreign countries is of course I think quite impressive, especially that we are living now very shortly after the COVID pandemic, so it's very nice to host it here in Warsaw, partners from 6 countries. To summarize, of course, it's impossible to summarize the scope of all speeches because they were all great. So we have the technical presentations, we have also managerial presentations. Yes, we have logistic topics. we have also a presentation of the research group of the Horizon 2020 project. So this scope proved that during this symposium you can have a lot of interesting presentations on many areas. So in the beginning, as I said yesterday, this project was dedicated mainly for the production engineering and aeronautical sector, but I think that you have proved now that the fields that we make researchers, that we make some our research efforts are much more higher than on the beginning we expected. So I think this is very, very positive. So of course I want from this place thanks very much from the Polish National Agency for Academic Exchange. So the NAWA, it was the funder of this project, and of course in this symposium. So without the support of NAWA, this symposium never can happen. So I think I should thanks very much, and of course I am a little disappointed that nobody from NAWA came here, but of course I understand. I talked with director of NAWA, and she explained to me that they have another meeting in Krakow, which was established much earlier. But of course she wants also thank you very much for the all attendance. So I think I also want to join to this thanks. And on the end, the one sentence I like very much, and after this meeting I think we should also remember about this, that the advancements in the technology field, so Industry 4.0, Industry 5.0 is very important. Yes, so I think that you see how fast is now technological progress in many fields, even in your lives, how many applications we used, yes, how our lives changing very, very fast. But I think that we should remember that we are the society, so we are humans, and of course we shouldn't forget about this. I am not a very big fan about the vision of the factory that the dark will be, control the human. I believe that the human should be in the center of this, so we should be center of this, so we should control, of course, the researchers, the industrial applications, so the technology and society should be in line, and of course we shouldn't forget about this. Of course, after these two, I hope, very fruitful days, I want to thank you for all attendance. I am very, very happy that you are here with me, with us. And of course, I also want to thank you for the organizing committee of this Symposium Industry 4.0. And on behalf of the Dean Chmielewski, I also want to thank you for the all online visitors of this symposium website, because I heard that the number of visitors is more than 100, so it's of course also very, very nice. Because I know that you are starving, I also, so maybe I will slowly finish this symposium. So thank you very much once again for the meetings, for the listening to the presentations, for the questions. And I officially announced that Symposium Industry 4.0 is closed. But of course, please don't leave this building. The lunch is waiting in room 341. So of course, please welcome and eat something, and then we can go to our duties or to home. So thank you very much once again, and it was a great pleasure.